For millions of people, a small device on their body works around the clock, doing the job of an organ. It's an insulin pump. But how does it deliver doses so small you could never see them, in a steady trickle that's not really a trickle at all? Let's open one up and see the tiny engine that runs a person's life, one whisper-quiet click at a time. To understand the pump, you first have to appreciate the organ it's replacing. A healthy pancreas is a master of quiet control. It constantly monitors your blood and releases tiny, precise amounts of insulin into your bloodstream 24/7. It's not a simple on-off switch. The pump's job is to replicate that incredibly sophisticated biological feedback loop using mechanics and software. The work has two main parts. First, a slow, continuous background delivery called a basal rate. This keeps things stable between meals and overnight. Second, short, larger bursts called boluses, which are delivered to cover the carbohydrates in a meal. The pump has to be a master of both the marathon and the sprint. And the scale of that background basal rate is staggering. These doses are tiny, landing every few minutes, all day and all night. Whether you're sleeping, working, or running a race, a single dose is far, far smaller than a drop of water. The hard problem here isn't just delivering insulin, it's metering these impossibly small volumes reliably into a moving, sweating, living person. Let's make the math friendly. Most pumps use what's called U100 insulin. That simply means there are 100 units of insulin in 1 milliliter of fluid. So one single unit is 1/100th of a milliliter, which is 10 microliters. To picture that, imagine slicing a single tiny raindrop into 5 separate pieces. One of those pieces is about 1 unit. Now for the part that reframes everything. A medium water drop is about 50 microliters. A fairly typical basal rate, say 0.8 units per hour, is only 8 microliters per hour. At that rate, the pump would have to run for more than 6 hours straight just to deliver the equivalent of a single drop of water. The precision required is immense. So how does the machine push such tiny amounts so accurately? It uses a positive displacement pump. That's a fancy term for a simple idea. Every time a part moves, it pushes a precise, fixed volume of liquid forward. There's no guesswork, no spraying, just a tiny calculated shove. Inside most tube pumps is a marvel of miniaturization. A tiny stepper motor, designed for exact, repeatable movements, gets a pulse of electricity. It rotates a precise fraction of a turn. This spins a finely threaded lead screw, which pushes a plunger forward by just a few micrometers. That's millionths of a meter. Each click of the motor moves the plunger less than the width of a human hair, delivering a perfect tiny packet of insulin into the line. Each click delivers a known dose, often as small as 0.025 units. To make sure that tiny packet only goes forward, the system uses check valves. These are simple one-way gates that prevent any fluid from flowing backward into the pump, even if pressure changes. Before the pump can push the insulin, it has to hold it securely. Inside is a reservoir, typically a small specialized syringe or cartridge, holding about 300 units. It's more than just a container. It has a plunger that must move smoothly without creating a vacuum, and the whole system is designed to minimize air bubbles, which are the enemy of precise microdosing. Every 3 days, the user carefully refills it. Yes. Some on-body patch pumps use a different kind of engine. Instead of a traditional motor and screw, some use a wire made of a shape memory alloy. A pulse of current heats the wire, causing it to contract and pull a lever. This motion turns a tiny gear train, which nudges the plunger forward. Different engines, same result. Tiny, precise packets. Here is one of the biggest surprises. The basal rate isn't a continuous, smooth drip like an IV bag. To achieve that incredible precision, most pumps deliver the basal rate in tiny micropulses. They deliver one small packet, maybe 0.05 units, then wait for 2 to 5 minutes before delivering the next one. Over the course of an hour, all those little sips add up to the hourly rate you programmed. In a quiet room, a pump user can often hear this process. Every few minutes, a faint, soft tick or whir sound. That's the motor engaging for a fraction of a second, delivering another pulse. It's the sound of the pump doing its job, one tiny packet at a time. From the pump's engine, the path is simple. The insulin travels from the reservoir, through a thin tube, and into an infusion set attached to the skin. The set has a tiny, soft plastic tube called a cannula that sits just under the skin. For a patch pump, it's the same idea, just without the long external tube. To make delivery reliable, the first step after changing a set is always priming. This process pushes insulin through the empty tubing to purge all the air, right to the tip of the cannula. The cannula itself might only need tens of microliters to fill, a tiny amount, but absolutely critical for accurate delivery from the very first pulse. But what if that path gets blocked? If the soft cannula kinks under the skin, pressure in the line will start to build. The pump's motor has to work harder to push each pulse. The pump's computer is constantly monitoring that motor force. If it exceeds a specific threshold for long enough, it knows there's an occlusion and sounds an alarm. This leads to a classic real-world story. It's 3 in the morning. An alarm beeps, waking the user. They check the pump, see the occlusion alert, and change out their infusion site. They prime the new set, resume the flow, and a dangerous rise in blood sugar is averted. It's a safety system that has to work perfectly every time. Now for the software. The pump's brain allows for incredible customization. A user can program different basal rates for different times of day. Many people experience a natural blood sugar rise before waking up, called the dawn phenomenon. They can program their pump to automatically increase the basal rate for a few hours to counteract it. The most modern systems take this a step further. They link the pump to a continuous glucose monitor, or CGM, that reads glucose levels every 5 minutes. This creates a closed-loop system. An algorithm, living either on the pump or a smartphone, analyzes the glucose data and predicts where it's heading. It then automatically adjusts the pump's micropulses to keep the user in range. This is called automated insulin delivery. Imagine a hiker on a long trail. As the sun rises, their glucose starts to climb. The system sees this trend and tells the pump to deliver a few extra micropulses. Then, as the hiker starts a steep climb, their muscles burn sugar faster. The system sees the glucose trend tilting down and automatically reduces the basal pulses, sometimes stopping them entirely for a short while to prevent a low. The hiker just hikes. The algorithm is the co-pilot. This technology is relatively new. The first hybrid closed-loop system was cleared by the FDA in 2016, with more advanced systems following in 2019 and 2022. The core idea is always the same. Use frequent tiny adjustments to gently nudge glucose toward the target, rather than reacting with large, late corrections. But even with this incredible mechanical precision, there's a wildcard: biology. The rapid-acting insulin used in pumps starts working in about 10 to 20 minutes and peaks around 1 to 2 hours after it's delivered under the skin. The pump's delivery is precise, but the body's absorption is variable. Heat, exercise, and even the specific location on the body can speed up or slow down how quickly the insulin is absorbed. This can have a bigger impact than the pump's own mechanical variance. That's why users rotate their infusion sites, are mindful of temperature, and change their sets every 2 to 3 days to ensure predictable absorption. Quick pause. If you're enjoying this look inside the machinery of everyday life, hit that subscribe button so you don't miss our next deep dive. Okay, back to the pump. So let's end by going back to that sense of scale. At a rate of 0.8 units per hour, a pump needs over 6 hours to deliver the volume of a single water drop. Over a lifetime, that tiny engine will meter millions upon millions of these whisper doses, quietly doing the job of a pancreas, one click at a time. One last thing, the exact pulse sizes, features, and safety checks vary between different makes and models. And real-world outcomes always depend on the user, their body, and their setup. But the core engineering principle is the same: a tiny, powerful engine, pushing tiny, precise packets run by smart software. If this gave you that, "oh, so that is how it works" feeling, subscribe and stick around. Buildguts digs into engines, chips, bridges, and the quiet tools like this that make modern life possible. Drop a like if this helped, and we'll see you in the next one.